Okay, I think we're all good. I'm happy to invite Diego Izquierdo to give a lecture on Miller K-theory and zero cycles over periodic functions.
So hello everyone, and thank you very much. So yes, we are going to talk about Miller K-theory and zero cycles over periodic function fields. And I'm going to start with some motivation of the problems we'll talk about. We start with the intuitive idea that if you take an equation with a large number of variables and with low degree over some fields, then it should have more chances to have solutions. This idea was formalized by Martin and Lamb, so by introducing the following definition. So let's take the field and let's I be a non-negative integer, and then we say that K is Ci if whenever you take X in P and K, a projective hypersurface of degree d with d to the I smaller or equal than n. So this is the inequality that tells me that I'm looking at an equation with low degree with respect to the number of variables. Then it should have irrational terms. Okay, so maybe let's see some examples and properties of these CI fields. So example, the first example is not really interesting, but should be mentioned. It's the case I equals 0. Well, the field is C0 if and only if it is algebraically closed. A is C0 if and only if K equals K1. Second, more interesting example that you've already probably encountered is Chevalier-Warning's theorem, which talks about finite fields. So Chevalier-Warning, which states that finite fields are C1. The third, a bit more complicated theorem is Zen-Land-Nagata's theorem, which is essentially a transition theorem that allows you to go from a field K to some of its extensions. So Zen-Land-Nagata theorem. What does it state? Well, let's start with the field K, which is Ci, and let's take K prime over K, the field extension with transcendent degree, let's say delta, and then K prime is Ci plus delta. Okay, and finally, I can show you the last theorem, which is also a transition theorem, but this time for formal power series. So this is probably the most complicated result here. It's Greenberg's theorem, which says that if K is Ci, then K double parenthesis T is Ci plus 1. Here, K double parenthesis T is just the field of Laurent series in one variable. So these are some examples. Of course, there are also counterexamples.
If you have more variables.
So if you have more variables, of course, if you look at, for example, K double parenthesis T double parenthesis this way, it's easy. The difficult thing is K double parenthesis T here. Yeah, I wanted to precise they are not the same. For this one, it's essentially unknown. Even with K equals C, this is unknown if it's C2. So some counterexamples. Well, the first ones are not very interesting, but should be mentioned. Take K, the field inside the real numbers, then you know sums of squares are non-negative, and so this tells you that K is not Ci for any number. The second more interesting counterexample is the case of p-adic fields. So p-adic fields. In fact, Artin conjectured that p-adic fields should be C2, and he got it wrong. It's even worse. So we have a theorem which is due well, in the first case to Tel-Aviv-Yaffo, and then to Arkhipov, Karatsuba, and Alemu, which states that, in fact, p-adic fields are not CI for any. All right. So these are all the examples and counterexamples, and essentially the idea today is to talk about some variants of these CI properties. Before talking about those variants, I would like to move to another area. I want to move to Galois cohomology. Why? Because when you look at these properties of the CI fields, in fact, they are very similar to some properties of Galois cohomology. So more precisely, if I look at Galois cohomology, well, I have an invariant, which is the cohomological dimension, which essentially measures the complexity of the cohomology of the field, and which is defined as follows. So the cohomological dimension of the field K is the maximum of the integers n, such that there exists a finite Galois module m, such that Hn of K with two efficients in m is non-trivial. Okay, so why did I introduce this invariant? Well, because it behaves in a very similar way to what I showed you here about the CI properties. Indeed, if I take a field that is algebraically closed, the cohomological dimension is 0. If I take a finite field, the cohomological dimension is 1. In the context of Zen-Land-Nagata's theorem, so I take the transcendence degree delta extension, the cohomological dimension of K prime is at most the cohomological dimension of K plus delta. And you even have equality if the extension is finitely generated. And finally, the context of Greenberg's theorem, you have that the cohomological dimension of K double parenthesis T is the cohomological dimension of K plus 1, right? And so when you see these parallel, you might be tempted to hope that there should be well, some connection between this cohomological dimension and the CI properties, right? So the naive question one may ask here is the following. If I take K a field, is it CI if and only if the cohomological dimension of K is at most 1? Well, I said this question is naive because one can easily see this is wrong. How? Well, one uses the counterexample that's here, p-adic fields. The answer is no, because if you take the p-adic field QP, we've seen that QP is not C2, but we know that the cohomological dimension of the p-adic field is equal to 2. So this contradicts the direction that goes from left to right, from right to left. And if you go in the other direction, well, the question is completely open. So it's a question to Serre. And there are essentially only two known cases, which are the case I equals 1. This one is easy. And the case I equals 2, which is hard, and which was proved by Suslin, well, in the context of the Bloch-Katos conjecture. And so for I greater or equal than 3, it's completely unknown. All right. So now the idea of what we're going to do next is to try to modify the CI properties so that they do characterize cohomological dimension. So let me erase. To do so, I will need one of the main objects that appear in this talk and that was on the title, and that's Milnor K theory. So we're going to talk about Milnor K theory. and the Kato and Kuzumaki's conjectures. Right, so I know that many people know what Melon-K theory is, but I'm going to briefly remind it. So the definition goes as follows. If I take K a field and Q a non-negative integer, then the Q Melon-K theory graph of K is defined in the following way. So KQ of K, it is just the graph of integers if Q is 0. And otherwise, we're going to take a quotient. So we take the Q-fold tensor product of K star over the integers. So here I have Q copies of K star. And in this tensor product, I mod out those pure tensors, x1 tensor xq, such that there exists I different from j, satisfying xi plus xj equals 1. So that's the definition, and even if it might seem a bit strange at first sight, you might find it natural if you think, for example, about Hilbert symbols when you work with periodic fields, or more generally when you work with quadratic forms. Something you should note is that these graphs might be a bit complicated to compute, especially because they mix the multiplicative structure of the field and its additive structure. Anyway, to modify the CI properties, I need one more structure on this Melon-K theory. I need what one calls a norm, so the norm map. What is that? Well, I'll take L over K, a finite extension, right? And let's start with the easy cases. So let's start with the case Q equals 1. What happens if Q is equal to 1? Well, the K1 of L by definition is L star. The K1 of K is K star. And well, you know that there is no map that goes from L star to K star. And L over K is just the usual, right? You can do the same thing as Q equals 0. Here, the K0 of L is Z. The K0 of K is also Z. And you have a normal map that goes from Z to Z, and that is the multiplication by the degree L over K. And well, the question now is, what can one do for higher degrees? What happens for Q greater or equal to 2? And well, this is not trivial, but Kato proved that there exists a norm map that goes from KQ of L to KQ of K, satisfying, of course, some compatibility conditions. I just want to stress that this is not trivial, it's really a theorem. Anyway, we can use this norm map from now on, and I'm ready to introduce the variants of the CI properties that we will be interested in today. So, definition. So 2 parts. The first part, we take Q a non-negative integer, which will correspond to the degree of the Melon-K theory we will be looking at. And I take Z over K, the variety. Then I define the norm group and Q of Z over K. So this is a subgroup of the Q Melon-K theory group of K. And it's going to be the subgroup that is spanned by the images of the norms. So here I take an L over K of KQ of L. Of course, I'm not taking all finite extensions out of K, but I will only take those over which Z acquires a rational point. Z of L is not it. Before showing you some examples concerning this definition, let me just do the second part. So now I'll take two parameters, Q and I, and here Q will be, as before, the degree of the minimal K theory, and I is the same as in the CI property. It's the one that will tell us to which extent we look at low degree hypersurfaces. And then we say that K is CIQ if, whenever I take L over K a finite extension, whenever I take Z in PNL a hypersurface of degree D with D to the I smaller or equal than N, well, if I have the CI property, essentially I would ask for Z to have a rational point. And here I'm going to ask a weaker condition. I will ask, in fact, that the norm group N cube of C over L is as large as possible. That is, it's just the whole minimal K theory group of L. In other words, minimal K theory should be spanned by images of norms coming from extensions over which my variety requires a rational point. Okay, so let's see some examples to try to understand that of these definitions. I think the good idea is to look at the extreme cases, so the case Q equals 0 and the case I equals 0. Let's start with the case Q equals 0. So in this case, well, what is the N0 of C over K? Well, this is a subgroup of the K0 of K, which is just Z. And it's the subgroup that is spanned by the images of the norms. But recall that the norm in degree 0 is just multiplication by the degree. So I'm looking inside C to the subgroup that is spanned by the degrees L over K, when L is a finite extension of K over which Z has a rational point. And so, if you want, this is also the subgroup of C that is spanned by the GCD of these degrees. Okay, and this GCD is what one usually calls the index of the varieties. Index of Z, and I will denote it by I of Z. Okay, great. So now if we come to the second definition, what does it mean? Well, the field K is CI0 if and only if what? Well, if and only if, whenever I take L over K a finite extension, whenever I take Z in PNL a hypersurface of degree D with D to the I smaller or equal than N, well, I'm asking that the norm group is the whole K theory group. So here it means that I'm asking that this index I of Z is equal to 1, right? I of Z equals to 1. Or if you prefer, this means that Z has points in extensions that have co-prime degrees, right? Or if you prefer, in the language of zero cycles, this means that there is a zero cycle of degree 1. In any case, this is of course weaker than having a rational point. So this is telling you that if K is Ci, then it is Ci0. Let's see the other extreme case. Now it's the case I equals 0. Right. So let's take I equals 0. And well, in that case, so in the second definition, I is equal to 0, so here the inequality T to the I is more equal than N is empty. It's always satisfied. So typically I can take just the point in the projected line. So I can look at the case where Z is the spectrum of some finite extension over L. Over L finite. Now if I look at that, well, what is the norm group N cube of Z over L? Well, essentially the fields over which Z has rational points are those that contain M. And so this N cube of Z over L is just the image of the norm map and M over L that goes from KQ of M to KQ of K, KQ of L, sorry. Right? And so now if I come to the definition of the CQ0 property, well, K is CQ, CQ0, if and only if, whenever I take the tower of finite extensions M over L over K, while the norm map in degree Q minimal K theory is rejected. Okay, so now when you see these two examples, essentially the moral you should take is that, okay, you have all these CIQ properties, and the smaller is I, the smaller is I and the larger is Q, the more K theoretic the property is, especially this one. And the more I is large and Q small, particularly in this case, the more the properties of Jeff entangled. Now the main observation that was done by Kato and Fusumaki in the 1980s is the following proposition. So I attribute it to Kato and Fusumaki in 86, but I mean, they did it assuming the Bloch-Kato conjecture, which is now known. And in fact, the core of the proof is the Bloch-Kato conjecture. I mean, essentially, once you have the Bloch-Kato conjecture, it's pretty easy to prove the right Bloch-Kato conjecture. And the proposition is that the field K is CQ0, so satisfies the most K-theoretic properties among the CIQ properties, if and only if the cohomological dimension of K is at most Q. In other words, this CQ0 property does characterize the cohomological dimension. And with this property, then they stated some conjectures. So here they are, conjecture by Kato Fusumaki in 86. The following, they expected that in fact all the CIQ properties would characterize the cohomological dimension. More precisely, that K is CIQ if and only if the cohomological dimension of K is at most I plus Q. In other words, the CIQ properties should only depend on the sum I plus Q. Well, that was their expectation. So if you just make a small picture, you have the CI0 property, the CI minus 1, 1 property, CI minus 2, 2 property, and so on, up to C1 I minus 1, C0 I. And well, by the proposition, you know that this last one is equivalent to cohomological dimension equal to I. I should not write after this line, so cohomological dimension equals I. Sorry, smaller equal than I. And well, they would expect that all these properties are the same, but they didn't know if that was true, right? Here in this picture, the more you go to the left, the more Diophantine you are. And the more you go to the right, the more K-theoretic you are. So sadly, Kato and Fusumaki got it wrong. So all these equivalences are wrong, in fact. And the counterexamples came a few years later. The first ones were by Tel-Aviv-Yaffo. So in 1989, sorry, there was a counterexample by Tel-Aviv-Yaffo. In the case of fields with cohomological dimensions. And then this was improved by Pouliot-Hélène and Mador in 1990. And in fact, they managed to find a counterexample in cohomological dimension. And so essentially, starting from these examples, you can prove that all these equivalences for any I are wrong. Right. So these counterexamples by Tel-Aviv-Yaffo, Pouliot-Hélène, and Mador are all constructed by some methods of transference induction. And in fact, you get fields that are extremely large that you essentially never encounter in arithmetic geometry. And so starting from here, there are two main questions that arise in this context. So which questions? The first question is whether one can prove the conjectures for some usual fields in arithmetic geometry. And here, of course, this notion of usual fields in arithmetic geometry is not well defined, but you can imagine that you start, for example, from p-adic fields, finite fields, algebraically closed fields, number fields, and then you allow yourself to take extensions of finite type or to take formal power series, this kind of stuff. The second natural question on the asked here is if one can modify further the CIQ properties so that they do characterize cohomological dimension. Okay, so in my talk, we're going to talk about a particular case of question 1. In the following talk by Giancarlo, he will talk about the second question. So maybe let me just say a few words about the first question. What is already known in that context? So already known, there's some results for for p-adic fields and for totally imaginary number fields. So all these fields have the homological dimension 2. That's the reason why I took totally imaginary number fields and not any number fields. So you expect that they do satisfy 3 properties. So you have the C02, the C11, and the C20. Well, the C02, you know, this is fine because that's just a proposition like Pattern automatically saw before. The C11 property is known. It's a theorem by Wittenberg in 2015. And as for the C20 property, it's completely open. So this one asks whether when you take a projective hypersurface of degree d with d squared smaller than n, it should have a zero cycle of degree 1. This is open. Over p-adic fields, it's only known for those hypersurfaces that have prime degree, and all other cases are unknown. And for totally imaginary number fields, there's not a single case that is known. Okay. The second kinds of fields we already know how to deal with are function fields of varieties over algebraically closed fields. So let's say complex function fields. Finite dimension. Well, they are known to satisfy all the expected CIQ properties. That's something I did a few years ago, 2017. All right. So now today's talk will be about another kind of fields. As you saw in the title, it talked about p-adic function fields. More precisely, we are going to talk about function fields of p-adic groups. Function fields of p-adic groups. Okay, so we start by introducing some notation. Let's take big K, the fields of the form little k of C, and here little k is a p-adic field. And C over little k is a smooth, projective, geometrically integral curve. Right, so typically, the basic example here would be the case where C is P1k, so that big K is the rational function field K of T. Right? All these fields turn out to have a homological dimension 3. Homological dimension of large K is 3, essentially just because the homological dimension of little k is 2, and you're taking the function field of curve, so you need to add 1 to the homological dimension. And so you expect the CIQ properties for I plus Q at least 3. That's what the Kato and Kuzumakis conjectures would tell. But there are some cases we already easily know how to deal with. That's whenever Q is at least 3, yes. Because you can use essentially the proposition of Kato and Kuzumaki. Kato-Kuzumaki's proposition implies that this case is open. If you're in minimal K theory of degree at least 3, everything is 1. And so we decided to look at the next non-trivial case, which is the case of minimal K theory of degree 2. So today we're interested in the case when Q is equal to 2. And so you want the C2I property for pi greater or equal than. That's what you would want. Now I can state the first theorem we got. So theorem A. So I'm going to take L over K, a finite and ramified extension of K, and I take Z over large K over I. That I will assume proper. So proper for I. Then, if you look at the quotient, so you take the K2 of K, and inside that you mod out the norms that come from oh, I forgot another notation. One extra notation, I take large L to be the field little l times large K. Okay, so it's a constant extension of large K. And then, if I look at the quotient of K2 of K by the subgroup that expands by the norms coming from large L, and by the N2 of Z over K, well, this is killed by pi K of Z E squared for every coherent sheaf E over Z. So here, chi K is of course the Euler pointer characteristic. So essentially, it's the alternating sum of the dimensions of the homology, heuristic homology of your coherent sheaf, right?
Z is geometrically integral?
No, does not need to.
What is LK? Is it a tensor conductor? Okay.
What is what?
You have L tensor K.
I mean, the curve is geometrically integral.
The rotation LK, LBK.
I mean, the K is the function field of C, not of C.
Rotation, little L is K.
You don't have a choice. I mean, it's this K is the function field of something that is geometrically integral. So it's the tensor product if you want, or we can.
C is LT or something.
The K is not the function field of C. It's the function field of C.
Yeah,
which is
geometric.
So Z does not intervene in this definition of big L.
They could intersect inside Z, function of Z may contain. Okay, so it's not may contain.
The function field of Z might contain.
Yeah, then perhaps the L tensor K.
Where? What? No. Well, we can talk about that after. We can talk about
What is F2Z over K?
this is the group that was introduced before by Katon Kuzmaki. So it's the subgroup of K2 of K that is spanned by those norms coming from extensions over which Z has a rational point. All right. So this is the theorem, and why is it interesting for us? Well, because it has the following corollary: the field large K has property C22. And I'm going to explain how one can deduce this corollary. So, proof. Let's take Z inside P and K. We need to look at a hypersurface with no degree, so with degree D, with the inequality, and since I'm looking at the C22 property, I have the inequality D squared smaller or equal than, right? Okay, I want to work with this hypersurface, and so the idea is first to observe that by theorem of Lang, the maximal and ramified extension of little k is C1. This is the theorem of Lang. And hence, if I apply the Zhang-Lang-Nagata theorem, it tells you that K and R of C is C2. Hence, Z has a rational point in this field. And hence, you can pass to the finite level and say that there exists L over K, finite and ramified extension, such that Z has a point in L of C. Right? And so I introduce the field large L, which is L of C, and this is the large L to which we will apply theorem A. All right. And so you have that K2 of K modulo the subgroup spanned by the norms coming from large L and the N2 of Z over K. Well, this is killed by the Euler-Poincaré characteristic of ZOZ squared. Right? But now, well, here, you know that Z has a rational point in big L, so this quotient is also K2 of K modulo N2 of Z over K, right? In fact, the norms that come from L are included in the N2 of Z over K. This is just because Z has a rational point. And at the same time, because C is a hypersurface of small degree, a finite hypersurface, in fact, you know that this Euler-Poincaré characteristic is equal to 1. Because Z is a finite hypersurface. And hence you're done. You proved that this quotient is trivial. In other words, K2 of K is equal to N2 of 0 to K. All right. So we have the C22 property. It's not everything we wanted to prove about the field large K, because if you remember, we wanted the C2I property for I greater or equal than 1. So the corollary tells us that this is okay for I at least 2, but that's still the case I equals 1. In fact, we should extend this result to hypersurfaces with degree Z with Z smaller than Z squared smaller than. So in that direction, we have theorem E, which states as follows. So I'll take little l over little k finite extension. This time I'm not assuming it's unramified, it's an infinite extension. I take z with large K a proper variety. And as before, I introduce large L to be little l times large K. Then there exists as greater or equal than 0, such that if you look at the same quotient as before, so k2 of k modulo the norms coming from L and the n2 of z over k, well, this is killed by following number. So I explained the notation steps afterwards. So here I have an integer, which is I run of c, times the Euler quantified characteristic of some coherent sheaf E to the S. So this for every coherent sheaf E over Z. So here there's one number I have not defined, and it's this I run of C. So I run of C here is what I call the ramification index of C, and it's in fact the GCT of the ramification indices of let's say finite extensions little k prime of little k, over which C has rational. This E of k prime for k is the ramification. All right. So in particular, for example, if C has a rational point, or even if C has a point in the maximal unramified extension of little k, this I run of C is equal to 1. And so this theorem can be applied essentially in the same way as I showed you before to get at least part of the C12 property for the field large K. So corollary, for any Z in P and K hypersurface of degree d smaller or equal than n, the quotient k2 of k by n2 of c over k is killed by IRM of C. And so in particular, we have that k2 of k is equal to n2 of c over k if, for example, C has a rational point in the maximal and ramified extension of little k. Of course, this is not completely the C12 property. To get the C12 property completely, we should get this result in all cases. Okay, if we get something that is weaker, we get that the quotient is killed by the ramifications. The proof of this corollary, as I said, is essentially the same as I wrote here. You just have to change a few things. So essentially here you start with the hypersurface which is T somewhere equal to that. And then you don't use this field K and R of C, but you use the field K bar of C, which is C1. And so this tells you that there exists a little k finite extension that might not be unramified, such that Z has a point of C. And then you do the same argument because the other quantitative characteristics. Great. So I still have 15 minutes more or less to talk a little bit about the proofs of theorem A and B. So ideas of proofs. Okay, So I'm going to start with theorem A. And what we will do is we're going to do it by steps, but I'm not going to start from the first step because I want to do other steps and then explain why we will make the first steps. Let's erase the whole board. And I'll have 5 steps. So, step 1, step 2, step 3, step 4, and step 5. And I will start with step 3. So the first, in principle, the first step would be to solve the problem locally. What do I mean by this? Well, we fix some x in K2 of K, and essentially we want to see that it's a product of norms coming from extensions of which our variety or our Bible surface with a degree has norms, right? And so I'm going first to solve this in a local setting. That is, I will take the the closed point of the curve. So this C1 is the set of closed points. C. And I take the completion of KFV. So I have the completion KV. And well, we prove here that X belongs to the subgroup spanned by the norms coming from our field large L that we fixed at the very beginning, and norms coming from some MIs. So sorry, I'm over V. So the norms coming from LV over KV. And then I take some extensions MI V over KV, and I look at the images of the norms. For here, some MIs such that MIVs such that Z has a rational point in MIV. Okay, so essentially I proved the very thing I want to prove over large K, but instead of working with large K, I work over the completions of large K. Okay, so this is step 4. Step 4 consists in globalizing these local extensions, the MIVs. Okay, what do I mean by this? Well, typically I mean finding extensions MIVs of this time the global field large K, such that we'll see as points in the MIVs, and well, I want typically that the completion of MIV at V is MIV, or for example, something that's a little bit weaker, NIV is contained in MIV. This kind of stuff. Okay. And this can be done thanks to a theorem that is Greenberg's approximation theorem. So Greenberg's approximation theorem allows to do this. All right, and once we've done these 2 steps, the final step is, of course, to go from local to global. So, step 5 is local to global principle. So, how does that work? Well, essentially, I want, I know by step 3 that, well, my X is in the kernel that goes from K2 of K modulo the subgroup spanned by the norms coming from L and the norms coming from the MIVs, sorry. K2 of MIV to the same groups local. So I take the product over, say, W in C1 of the same thing. So K2 of KW divided by norms LW over KW of K2 of LW to and the norms from the NIVs completed at W over KW of K2 of NIV double. Okay, essentially I just wrote in another way what I proved in step 4. I will call this kernel the SHA-N2. SHA is Station for H. And then the idea is to use a duality, a quatutate duality. So there is a quatutate duality in this context that allows you to compute the SHA-N2. So essentially, SHA-N2 is dual to some SHA-2 of T hat for some finitely generated Galois module T hat. Okay, and essentially we need to, in order to compute this SHA-N2, to compute this SHA-2 of T hat. There's one thing that is a bit different from the usual quatutate duality over number fields, and it's that, well, written like this, it's not completely true. I need to put a bar on this SHA-2 of T hat because I need to mod out the maximal divisible subgroup in SHA-2 of T hat for this duality to be true. Okay, so here, SHA-2 of T hat bar is SHA-2 of T hat modulo the maximal divisible group. And so essentially to prove that this SHA-N2 is trivial, I need to prove that this SHA-2 of T hat is divisible. Okay, and well, typically to try to do that, well, what we are going to do is to look at SHA-2 of T hat and then try to compare it typically to the SHA-2 of L T hat by restriction, and for example, the SHA-2 of the NIVs T hat. Okay, typically we look at this map by restriction and then we try to study it. This is quite technical and quite complicated, but what you see here is that on the right side, these T hats essentially split over the fields you're looking at. They become quasi-trivial. And so here, essentially I have SHA-2s of Z, okay? SHA-2s of Z over some finite extensions of large K. SHA-2 of Z under over a number field is always 0. That's Chebotarev. And that does not hold, okay? You might have that SHA-2 of Z is non-trivial. So the problem here is lack of Chebotarev's theorem. In fact, the SHA-2 of Z is in general different from 0. And this gives you a lot of problems to manage to prove what we want to prove. And for that reason, essentially, we need to, in some sense, avoid, in this context, counterexamples to Chebotarev's theorem. And that's why, in fact, my previous steps, I have to modify them so that I choose the NIVs wisely, not just as I did. And that's also why I will need steps 1 and 2. So all the problem here comes from this Chebotarev theorem. So let's come back. Let's come back to step 4 first. So here in step 4, we need something finer than doing this. We need, moreover, that the NIVs are linearly disjoint from fixed finite extension of K, which essentially contains counterexamples to Chebotarev that we want to avoid. Okay, and if we want to do this, we cannot use any more Greenberg's approximation. We need to do something different. And to do something different, the first thing one has to do is to do step one and reduce by a délissage due to Greenberg to the case when Z is smooth. We reduce to the case when Z is smooth, and then by combining this smoothness together with Hilbertianity properties of the field large K, you manage to do this finer step forward. So this is the first thing one needs to change. The second thing is that you might have some, let's say, counterexamples to Chebyshev that come from the fact that your curve has what I call residual index different from 1. So that's step 2. You might look at the residual index of the curve C, which is the GCD of the residual degrees on the curve. Okay. And essentially, to be able to avoid all the Chebyshevs, all the counterexamples to Chebyshev you want to avoid, you do not only need to do what we did in step 4, but you also need this IRS of C to be equal to 1. And so step 2 is exactly a step to reduce to the case when IRS of C is equal to 1. And how is this done? Well, the idea is so how I explained it. Yes, the idea is to take K prime with a little k and finite and ramified extension, and then prove that the norm map that goes from little k prime times k over large K, and so this goes from k2 of k prime k to k2 of k, is rejected. And if you prove this, this allows you to reduce to the extension little k prime k. Okay, you can replace large K by these fields little k prime large K. And so if you take little k prime to be the unramified extension of little k of degree I cross of C, essentially you've reduced to the case where the residual index of the curve is equal to 1. Finally, to prove this surjectivity, essentially you use the local global principle, but which is a bit different from the one that we saw there, because if you look at the local global principle we did here, it was with respect to these places that come from, well, closed points of the curve C. Here, to do the local global principle you need to look at a larger set of places. Essentially, the set of places coming from 2-dimension 1 points of the smooth, of the regular model, of the curves. And once you've done all these steps, then you get your results. I think we have 1 minute. Sorry?
You want to release some time for questions?
Oh, yes, yeah. Okay, then I stop here.
I'm very happy because I don't think I understood what BBL is.
I have a technical question regarding step 4 about this quantitative duality. Is it a new instance of this duality, or you use something which was written in your earlier papers in Harari-Samanelli or whatever?
So it's not a theorem by Harari-Samanelli. It's not either something in this paper, it's something I did in my PhD. It's essentially the thing is that Harari-Samanelli have duality, positive duality of these kind of fields, but essentially you take the torus T, you take the dual torus T prime, and they have a duality between notation for average groups of these two. So if I'm not mistaken, it's between Shala and T and T prime. But here we don't want dualities for these objects. We don't want for the torus, in fact. We want the duality for instead of the torus, we want to replace it by something well, which is written usually like this. It's essentially something that is computed thanks to mutillic complexes. Essentially because tori will allow you to deal with the K1, but here we want to work with the K2. So you need mutillic complexes. So you need a quadratic duality for mutillic complexes. And that's typically coordinated from the
Since there's a result about K2, is there a way to translate this to statements about simplest algebras? Let's give us something interesting.
I haven't really thought about it.
I mean, probably you can write if you assume half numbers. I'm not sure it's really interesting to write it that way.
So let's take a 5 minute break.